Okay, so the note here, AC versus DC. Well, AC, alternating current, DC, direct current. The difference is what's happening on this end. If we've got power coming from the wall, DC, which you won't have in your home, probably. If you're watching this, you don't have DC coming out of your wall. It would go straight through one direction, all the way through, constant resistance. What would happen is that magnetic field would build up in these guys, and it would stay because it's the same direction of the current continuously. AC is the opposite. On this guy right here, we got alternating current. Current goes in, increases, changes direction, so it tapers off, goes back down, and then reverses. So the magnetic field reverses direction every time it changes. But this is what you call a universal motor. Since we're sending that current through here, it doesn't matter. The field on this guy is always going to be opposite the field on this guy. So what that means is when the AC goes one way, the field on this guy goes the other, and when it transitions, the field going this way, now this one goes the other way. So they're always opposing, except there's a period of time when the fields are tapering off and reversing direction, so they taper off and build back up. So that has some effect on our current. Isn't really continuous, and I won't get into that because I don't really understand it. Maybe somebody else can explain better than I can with lots of nice infographics. But what happens then if there's a lot of on off on off on off? Well, that 120 volts isn't really 120 volts. You got 0 volts, you got minus volts, you got plus volts, and actually that 120 is what they call the root mean square. Think like average. So actually you may have a bigger voltage difference than that. Now I won't quote any figures. I will get it wrong, but trust me, what's going on here has more potential, more zappy zap than 120 volts sometimes, and then a lot of the times it's less. So what does that mean? Well, that means we've got higher and lower current going up and down, higher and lower magnetic fields going up and down, up and down. If this tool were DC, 100% all the time, same magnetic field here, we've got full current going here, and now this magnetic field, every time it moves over one of these guys, or however many they are, it's going to shift the field. And I'm cheating here, but 1, 2, 3, they're all numbered. So we know we've got 16 poles. So 1/16 of 360 degrees is however many that angle is. We know that magnetic field only has to kick over a little bit. So it's not that total charge, discharge. It's not the same amount of resistance that you get from that 180 degree AC flip, which means our average current, 115 volts AC, probably less than if we had 115 volts DC. Now, if you can go find 115 volts DC, you will probably burn this right up if you don't kill the switch first. But I have a feeling the heat will be pretty intense. Actually, good point about heat. See the laminations? We got these striations, the lines in the metal, lines in the metal. What they do is they stack up these plates. They are, well, they're welded, so I guess they're electrically connected. I don't know if that's intentional, but they've got some kind of coating, a little glossy here, so that keeps them insulated from each other. So this guy conducts the magnetic field, contains it inside the case, focuses it on the motor, if you can imagine. Same thing here. We're keeping that magnetic field aligned in the direction we want to go while giving us a way to wind the wires how we like them. You can see that they double back on themselves at the top. So we get a few loops, and then it goes around the other side and a few loops and back out the other contact. So the reason for that is every time we change the magnetic field, it's built up inside this guy, and we get current flowing in this from just magnetic field. It's all insulated from the wires. But if these were continuous, solid, you get what they call eddy currents. Every time that changes direction, you've got a flow, and instead of just flowing through thin plates, it's now able to do other directions, electrons bouncing off of each other. It's like electron pinball. not good. It generates heat. If you can think of friction, resistance, these things bouncing around in there, heat, collisions. Same theory over here. Same striations, same construction of stacked metal plates. Well, what about DC? This, we don't have any changing fields, so I mean, it matters once you plug the thing on, flip the switch, it powers up, so it keeps all those electrons moving in the same direction one time. Field stays in the same direction the whole time. Over here, that's a little bit different story. The field keeps kicking over, but it's always in the same direction, so the current flow in this guy is small and relatively slower than the 180-degree flip. So these things keep down our electron collisions. They keep down eddy currents in an AC function. They don't really do all that much in DC. But at the same time, again, same for same, 115 volts DC, this guy is probably going to move way more current because it's got way less resistance. Remember, we're talking about AC is average. It's more, there's less. A lot of times there's less. This guy over here, you know, same thing. DC, all the same direction. Current's only moving a little bit. So we get less impedance, more current. So don't go hooking this guy up to 10 car batteries. You know, I think 2 or 4 will be a terrifying amount, you know, and probably 1 will push enough current to use the tool. 2 will probably be moving more current than this thing sees coming out of a wall outlet. Somebody out there, go calculate. Tell me I'm right, tell me I'm wrong. You know, show us how it works. That'd be great. So that is, you know, a tool motor, a universal motor from the perspective of a guy who doesn't really understand. You know, he knows just enough to be dangerous to himself and others, and who just, you know, looked at where the wires went, measured where the connections were, and called it good. So, yeah, don't quote me on that, and don't bet your life on it. Thanks.